let G and G bar be groups. A function, go ahead and use the same notation, phi from G to G bar is called a homomorphism rather than an isomorphism if phi is operation preserved. I.e., again, phi of AB equals phi of A times phi of B for all A and B in G. And if I ask you on the exam to define a homomorphism, you should say what operation preserving means once more, at least. We know what it means from isomorphisms, but I want to emphasize it enough to say you should be able to put that on there. Nothing about being one-to-one or onto. Okay. Homomorphisms don't have to be one-to-one. They also don't have to be onto. In fact, given any two groups, there's always at least one homomorphism from the first group to the second group. It's called the trivial homomorphism. It's an example. The trivial homomorphism phi from G to G bar, where G and G bar are any groups, is defined by the equation phi of G equals E bar for all G in G. I suppose we should verify that that is operation preserving. Check that. Phi of AB, where A and B are in G, is E bar, the identity of G bar. And phi of A times phi of B is E bar times E bar, which is E bar. Done. So if you map everything in the domain to the identity element of the codomain, that's a homomorphism. And if G and G bar are any groups, you can always define such a homomorphism. Okay, the trivial homomorphism. Linear transformations of vector spaces are homomorphisms. Because remember, vector spaces are groups under addition if you ignore scalar multiplication. The zero vector is the identity under addition. If the linear transformation maps everything to the zero vector, that is a homomorphism. It's this homomorphism, the trivial one. Its matrix is the zero matrix. All zeros would be the trivial, would be a matrix that defines a trivial homomorphism of vector spaces. I'm talking about Rn and Rm, not abstract vector spaces. Okay. What concept in linear algebra was one of your favorite concepts about linear transformations? I say favorite with a big smile on my face. Maybe it wasn't such a favorite. Starts with a K. I'm thinking of something that starts with K, the word K. Letter K, a word starting with K. Reminds you of food, like popcorn. Kernel. Remember kernels in linear algebra, your favorite subject? Find the kernel of this linear transformation. Guess what? They come back. Definition. Given a homomorphism phi from G to G bar, the kernel of phi, ker phi, what was it in linear algebra? It was the set of all vectors that got mapped to the zero vector. What's the analogous idea here? The set of all group elements in the domain that get mapped to the identity element of the codomain. That's the kernel. Note, if phi is the trivial homomorphism, or I should say a trivial homomorphism, because it depends on what G and G bar are. Then the kernel is the entire domain. Why do we talk about kernels in linear algebra? Same reason we talk about null spaces of matrices. You're trying to solve systems of linear equations. Null space of a matrix is the solution set of a homogeneous system of linear equations where you get a bunch of zeros on the right side, which is always at least one solution. The kernel always exists. There's always at least one vector in the kernel of a linear transformation. There's always at least one group element in the kernel of a homomorphism, the identity. In fact, the kernel of any homomorphism, you might guess, is a subgroup of the original group. In fact, it's a normal subgroup. Hey, let's do a little proof. Let's prove kernel is a subgroup of G and in fact also a normal subgroup. So we'll do both a subgroup test and a normal subgroup test. Oh, this could show up on the exam. Okay. Claim the kernel of a homomorphism is a normal subgroup of the domain. Could we just get away with doing the normal subgroup test and not have to bother doing the ordinary subgroup test? Well, if you look at the normal subgroup test, part of the hypothesis is that you already have a subgroup. So you really have to do two tests if you're going to fully do this. We should first note that the kernel's not empty. I already mentioned that. We know, okay, well, we know, quote unquote, we haven't actually proved this. Yeah, we've proved that isomorphisms map the identity to the identity. Do homomorphisms? Yes, they do. Haven't actually proved that. But if you look at the proof that the isomorphisms map the identity to the identity, you never use the fact that the isomorphism is one-to-one and onto. Let's see, where is that proof here? If I can pick up the book here. This is chapter 6. Let us denote the identity of G by E and the identity of G bar by E bar. E equals E times E. Boy, I think they make it more complicated than they need to. E bar times phi of E, because E bar is the identity of G bar, does equal phi of E. And yes, E equals E times E, so this is equal to that. And then phi is operation preserving, so it equals that. And then they do right cancellation to say E bar equals phi of E. They never use the fact that phi is assumed to be one-to-one and onto there in the isomorphism chapter. So this is just using operation preserving, so it still works for homomorphisms. Okay. We know phi of E equals E bar. So the kernel of phi is non-empty. Oh, I better use the other symbol for the empty set, because it looks too much like phi. Well, maybe I can make it more round like that or something like that, but with a slash that's a little more slanted, but whatever. Ignore. So the kernel is not empty. Let's try the one-step subgroup test now. Let A and B be in the kernel of phi. You've done this a lot. We must show that A times B inverse is also in the kernel. Well, plug it into phi. The fact that phi is operation preserving allows us to write that. And it also allows us to write this. Technically, we haven't proved that yet for homomorphisms, but we did prove it for isomorphisms. And once again, if you look back at the proof for isomorphisms, you never use the fact that the isomorphisms are one-to-one or onto. Operation preserving is enough for this. Phi is OP. A and B are assumed to be in the kernel, so this is E bar times E bar inverse, which is E bar times itself, which is E bar. Done. Therefore, AB inverse is in the kernel. Therefore, the kernel is a subgroup. But it's also normal. Now prove normality. And by the normal subgroup tests, let's go ahead and use an X. Let X be in G. We must show that the set X, H, X inverse, where H is the kernel. That's my H there. It's good enough to show it's a subset of H itself. It's good enough to show it's a subset of the kernel. And actually, if it's a subset of the kernel, it'll actually equal that, but you don't have to show that. This is called a conjugate of H, conjugate of the kernel. It's always a subgroup of the group as well, but it's not necessarily always a subset of H, the kernel in this case. But with normality, it is. By the way, you should be able to show conjugates in general. X, H, X inverse are subgroups of the group as well. I put those kinds of problems on exams. It's a subgroup test. It's not necessarily always equal to H. It's not equal to H if H is not normal. But it is equal to H if H is normal. And this normal subgroup test says if you can show it's just a subset, that's good enough. So let's say, Y be in this conjugate of the kernel. We must show Y is in the kernel. What does it mean to be in this set? It means that there exists some element G of the kernel such that Y equals X, G, X inverse. That's what this set is. It's the set of all elements that are the products of the form X times something in the kernel times X inverse. Well, it's going to be pretty easy. Phi being OP will do it for us. And the assumption that G is in the kernel. This is phi of X times phi of G times phi of X inverse. G is in the kernel of phi, so phi of G is E bar. I can also write this. Didn't need that extra set of parentheses. Which is this. Which is this. Done. All right, so if you're real clear about what you need to do, and you've practiced these kinds of things enough, the answers fall out pretty quickly. Praise the Lord, we are done. Homomorphisms have plenty of other properties, and we will look at those. Before we do, let's look at the most important thing related to homomorphisms and kernels. It's got the fancy sounding name of first isomorphism theorem. Wow, sounds fancy, sounds important. And yeah, it is pretty important. And it is pretty fancy, I guess you could say. Let phi be a homomorphism from G to some G bar. There's a couple different ways this could be stated. And I'm forgetting actually offhand which way the book states it. You could either assume phi is onto and state the conclusion in a certain way, or you can not assume phi is onto and state the conclusion in a slightly different way. But they are equivalent to each other. I forget what the book does. Let me glance at it here. The author does not assume phi is onto. Just that it's a homomorphism. By the way, we've got these different names now. Isomorphisms. We had also automorphisms and interautomorphisms, and now we have homomorphisms. There's more where these come from. There are also monomorphisms and epimorphisms. What's a monomorphism? A monomorphism is a homomorphism that's also one-to-one. Mono, one. An epimorphism is a homomorphism that happens to also be onto. Fun with names. You might as well give something a special name. Makes it feel special. So this is a homomorphism. That's the only assumption where G and G bar are, of course, groups. That's a background assumption. I'll just say homomorphism of groups. The conclusion is, the kernel is a normal subgroup of G. What do we do with normal subgroups? In chapter 9, we form some other kind of group. Say it loud and strong. Factor groups, also known as quotient groups. So we form the factor group of G by the kernel, G mod the kernel. This is called first isomorphism theorem, not first homomorphism theorem, first isomorphism theorem. This must be isomorphic to something. Yeah, it's isomorphic to the image of G under phi, the direct image. Remember what this is. This is the set of all outputs of phi. And if phi happens to be onto, it's going to equal all of G bar. So another way to say this theorem that I hinted at is that if phi is a homomorphism that's also onto an epimorphism, then this factor group is actually isomorphic to G bar. This equals G bar if phi is onto. Of course, did you know you could always make a function onto if you want to? Hey, that rhymes. You can always make a function onto if you want to. What am I talking about? How can I always make a function onto if you want to? Any function, even the trivial homomorphism, you can make it onto. What little sleight of hand can you do? Just change the. You awake? Function, domain, codomain. just change the codomain. That's all you have to do. Like the trivial homomorphism, just change the codomain to be the trivial group, just ER by itself. Then it magically becomes onto. Okay, it's just a matter of perspective. Oh, how in the world would you prove this? I don't want to do a full proof, but let's think about it. I think I do a full proof in one of the lectures. Let's just think about it. I'd have to come up with a map with an isomorphism from this factor group to that set. And that is a subgroup, by the way, of G bar. Equals G bar if phi is onto. Even if phi is not onto, it's a subgroup of G bar. It's a subgroup of G bar in general. Come up with a isomorphism from there to there. So, I'll call this idea of proof. Oh, what should we call it? How about our other favorite Greek letter in this course, psi? I mean, there's alpha and beta too, but okay. Come up with an isomorphism from this factor group to this domain, this direct image, the range of V, if you prefer. I want to define psi by what kind of formula? If you've been really working hard at trying to understand many of the proofs in the book, in chapters 7, 8, 9, and now 10, what I'm about to do should feel fairly natural. Give me an arbitrary coset in the factor group. G curve, right? That would be an arbitrary left coset. Elements of the factor group are left cosets. What is like the only thing you could map it to in there that makes use of these symbols? Oh, how about phi of G? That's got to be it, right? What else could it be? Just like I was emphasizing earlier today with your CP. Like, that's the only thing that makes sense to even try. If you understand the abstract ideas and understand, for example, the elements of this are left cosets, and the elements of this are outputs of phi, that's the only thing to try. But once again, we got this issue. What if you have a different coset representative? You have to show psi is well defined. That's part of the proof. I put that in exams before. Maybe I put the full proof on exams before, but I know for sure I've at least put the proof that psi is well defined in exams before. Because there's two important things going on there. There's first of all the realization that you need to show it's well defined, that the same coset can have different representatives. You know, what if there's a G1 that's the same left coset? Is phi of G equal to phi of G1? Does this mapping make sense? And then showing that is good practice with properties of cosets, for example, and also in this case, understanding what the kernel is. So I'm not going to do the details here. Is for you to think about, show it's well defined. You'd have to do 4 things really. You'd have to show it's well defined, one-to-one onto an operation preserver. It's definitely onto. Give me something in there, an arbitrary thing in there looks like that for some little g and capital G. So this maps to that. Onto is the easiest part. One-to-one operation preserving, a little harder. Probably OP is the hardest one. Well, no, actually, that's not. One-to-one's probably the hardest one. And actually, I think what happens is 1-to-1 is the reverse argument of showing it's well-defined. First place. I think that's what happens. Okay, so I'll let you think about that. I would encourage you to see if you can do it on your own. Something else related to this I also want to mention that also comes up in the lectures is that these kind of function diagrams often get expanded into what are called commutative diagrams. This is actually a big thing in what's called homology and in general category theory, which is that abstract nonsense stuff. This diagram often gets expanded, and I usually draw it like this. Put the group itself, G, up here. Draw an arrow to G bar. Well, scratch that out. Draw an arrow to phi of G, which is a subgroup of G bar. Put the factor group of G by the kernel of phi down here. G mod the kernel of phi. This psi function that we just defined is a mapping like this. And then you complete the diagram by drawing one other arrow going down like this. My abstract algebra teachers always called this mapping pi. But I think our book, if I recall correctly, uses the symbol gamma for this mapping. What is that mapping? It's not, if you call it pi here, it has nothing to do with the number pi. I think they used the letter pi because pi in English starts with a P, and projection also starts with a P, and this is kind of like a projection. What does that mean? Well, it's kind of like this picture. Kind of. Like this picture in the book. This one happens to be a homomorphism from S3 to Z2. Kind of like that picture. Maybe I shouldn't overdo it. In that, in the sense that G bar is kind of like a bigger group. Maybe, or G has a bigger group than this. G might have, 100 elements, order 100. Maybe the kernel has 10 elements, order 10. Lagrange's theorem then would say this factor group has 100 divided by 10 elements, 10. It's smaller than the original group. And that's a theme, actually, the author tries to bring up in the reading in chapter 9, is that factor groups are, unless the subgroup is trivial, they are smaller than the original group. And but they still reflect some of the properties of the original group. It's sort of like an image of the original group. It's sort of analogous to, think of a three-dimensional object in space, like a cube. And if you project it down onto a two-dimensional surface, like look at its shadow, you see parts of the image, but not the full image. Maybe if you rotate the cube, you can tell how, as the shadow changes, that this really is a cube in 3 dimensions. That's a projection. It's like a projection in linear algebra, actually. Projecting vectors onto subspaces. That's why this is often called a projection, and since projection starts with P and pi starts with P, I think that's why they use the letter pi there. But what is it? What is that mapping? This, by the way, is the original homomorphism right there. Pi of an arbitrary element of capital G maps that element to the left coset containing that element. Pi is sometimes called a natural mapping from G to this factor group. And we also say this diagram commutes, and you'll see people put these like lines in there. This means diagram commutes what does that mean? It means that if you start in G and you want to end up in phi of G here, you can go through the diagram in either way and you'll end up at the same spot. You can either just apply phi, or you can apply pi then psi. It means phi equals psi compose pi. Where I put the circle there for function composition, though, you know, it's traditional in our book not to bother. It commutes because you can go either direction through the diagram and you end up at the same spot. This takes proof. Is the proof hard? No, it's not that hard. What's psi compose pi of an arbitrary element of capital G? By the formula for pi, it's psi of the left coset G cur phi. But we know that is phi of G from the definition of psi. Done. That's the definition of psi. This equality right here is the definition of pi. Not the number pi, but this projection mapping. And yeah, if you get into homological algebra, and what is homological algebra? Well, there's a purely algebraic version of homological algebra, and there's also an algebraic topology version. Homological algebra, maybe we should look it up just for fun. You're applying, in algebraic topology at least, you're applying algebra to topology. Homological algebra. And the subject is full of these commutative diagrams. And so I took an advanced algebra class in grad school, graduate level class, where the majority of the class was homological algebra. And we had all these diagrams like this all over the place. This is related to my hardest math class in the world video. That was about what are called spectral sequences. Spectral sequences are related to homological algebra. You've got these groups all over the place and these arrows all over the place. And the hardest part about it is you just don't know what it all means. Like, what does this all mean? Oh, and there's that word. Where is it? I lost it. Functors. Ext functor. Functor is such a fun word. Hardest stuff, there we go, spectral sequences there, that's homological algebra. The hardest part about it is knowing what it all means. But actually, at the most basic level, when you're doing simpler diagrams like this, the proofs you end up doing end up actually being fairly easy. Because it's just sort of follow your nose kind of stuff. And you just do the only thing you can do and it pops out. Kind of like what I'm talking about with this example is you kind of just do the only thing you can do and the result pops out. Even though it's super abstract and you don't really know what it means, doing the proofs themselves is not that hard in the end. I'm not saying this is easy when I say that. I'm just saying what I said. which sounds like I'm saying it's easy. The difficulty is in the abstraction and understanding how it's all relevant for anything else. Once you get used to that abstraction, you just do the only thing you can do and the results just sort of pop out. Doesn't mean you could discover them in the first place very easily, but if you're told do this, then you just dutifully do it and there it is. Okay. But as I keep emphasizing, this is very relevant for studying groups.